Isn't it kind of wild how your phone just knows your face? Or how some cars can drive themselves and spot a pedestrian? We totally take it for granted that computers can see things, but the process behind it is, well, it's just incredibly complex. So, how do they actually do it? And more importantly, can we make them do it even better? Let's get into it. So, how in the world does a computer look at a detailed, colorful photo like the one on the left and turn it into the simple, clean line drawing you see on the right? This is one of the biggest questions in all of computer vision. And, as our need for speed and efficiency just keeps growing, the real question is, can we find a completely new, a radically better way to get this done? Well, the secret is a process called edge detection. The best way to think about it is like this. It's how a computer makes a sketch. It scans the image and finds all the spots where the brightness or the color changes really fast, like the brim of a hat or the curve of a jaw. That creates a basic outline, and that outline is the absolute first step for the computer to start identifying shapes, objects, and pretty much everything else in the picture. Now, this isn't some old, settled science. This is a massive area of research happening all over the world right now. You've got experts like Professor Bhaskar Gar at the University of Alabama in Huntsville who are working at this amazing intersection of artificial intelligence and quantum computing, and they're really pushing the limits of what we thought was possible. For years and years, the way we've tackled edge detection has been based on what we call classical computing. That's the same kind of processing that's happening inside your laptop or your phone. And these methods, they work, they're well understood, but they're definitely starting to show their age. Yeah, as our demands just get bigger and bigger, this old way of doing things is hitting a serious wall. It's creating this major processing bottleneck. Okay, so take a look at this. This is a simplified diagram for a super common classical method called the Sobel operator. Now, don't worry about reading every single box. Just look at how many steps there are. It's this long sequential process. The computer has to line up the image, do all this complex math, shrink the data, compare it to some preset value. It's just a lot of work for every single frame. And this is really the heart of the problem. The researchers who wrote the paper we're digging into today summed it up perfectly. These traditional methods are just slow and power-hungry. They demand a ton of computational muscle to get the job done. So who cares, right? What's the big deal? Well, when you're talking about applications where every single millisecond is critical, like a self-driving car that needs to spot an obstacle right now, or a surgeon who's relying on a live medical scan, this bottleneck isn't just some small inconvenience. It can be a massive point of failure. We need something faster. We need something better. And that brings us to the hero of our story, a totally different way of computing that could just shatter that bottleneck. Let's talk about the quantum advantage. Okay, so the difference here is fundamental. It's how these computers think. A classical computer bit is like a light switch. It's either on, which is a 1, or it's off, a 0. Simple. But a quantum bit, or a qubit, is on a whole different level. Thanks to this mind-bending property of quantum mechanics called superposition, a qubit can be both a 1 and a 0 at the exact same time. Think of it like trying to solve a maze. Classically, you try one path, hit a dead end, go back, try another. With a quantum approach, it's like you could explore every single path all at once. And this amazing ability to chew on massive amounts of information all at once, that's called quantum parallelism. And it's exactly this property that makes quantum computers seem almost tailor-made for ridiculously complex jobs, like analyzing every single pixel of an image at the same time. So, armed with this incredible new toolkit, researchers came up with a brand new recipe for edge detection. Let's take a look at how it works. Hey, remember that complicated, multi-step diagram we saw for the old classical method? Well, look at this. The new quantum approach is so much more direct, almost elegant. The image data goes in, the quantum system does its thing, and boom, the edge-detected image comes right out. It's just a much cleaner, more powerful process. Now, the secret ingredients, the things that make this new recipe work so well, are these highly specialized quantum components. You can think of them as custom-built tools, designed specifically to let the quantum circuit run its calculations with just incredible efficiency. So this is basically the engine under the hood. Now, don't freak out. You're not meant to understand this whole circuit diagram. It's just here to show you the powerful, complex quantum machinery that's running that simple 3-step process we just saw. This is where the real magic happens. Okay, so the new quantum recipe, it looks amazing on paper, right? It's elegant, it's powerful, but does it actually perform better? Let's check out the head-to-head results.
So the researchers tested their new quantum adder against a conventional one. The things to look at here are loots and slices. That's just a way of measuring how much physical hardware the process needs. And then there's overall delay, which is exactly what it sounds like, speed. And for all of these numbers, lower is better.
And here it is, visualized. When you look at how many resources it uses, the new quantum method is the clear winner. I mean, it uses over 20% fewer resources. That means it's more efficient and could even be cheaper to build. Now for the big one, speed. And yep, you can see it right there. The overall delay is lower for the quantum method. So not only is it more efficient with space, it's also over 5% faster at actually doing the work. So the data really speaks for itself, doesn't it? The verdict is clear. When you look at the key metrics, how efficient it is and how fast it is, this new quantum-based approach just wins. It's a total win-win. But look, this is way more than just a cool result in a lab. So what does a breakthrough like this actually mean for the future, for the real world?
Well, the potential applications are just massive. I mean, think about medical imaging. Faster, more precise edge detection could lead to way better, earlier diagnostics. Or what about autonomous vehicles that can recognize threats and objects in the literal blink of an eye? This could improve everything from real-time security systems to the entire next generation of robotics.
So the main thing to take away from all this is that it's not just some small incremental improvement. This research is a foundational building block. It's a huge step toward creating a new kind of computer vision that is fundamentally faster, smarter, and way more efficient than anything we've ever had. We are giving our machines a much better way of seeing, of perceiving the world around them in a way that's closer to our own. And it really leaves you wondering, doesn't it? Now that we're getting so much better at teaching them how to see, what's the next great frontier in teaching them how to truly understand?